Hello everyone. So today we are going to share some information about eigenvalues and eigenvectors. So our group members are Arya Shevade, Smart Shinde, Harshal Shirude, Jay Sindwa, Ojas Sonar, Janvi Sonar, Kaushal Sonje, Altaf Tadvi, Shruti Thete, Arya Thomre, Sharvari Tungar, Sneha Vadgule, Samruddhi Wagh and Raj. So, the topic which we are going to cover are eigenvalues and eigenvectors, Cayley-Hamilton theorem, diagonalization of matrix. Course outcomes: the essential tools of matrices and linear algebra in a comprehensive manner for analysis of systems of linear equations, finding linear and orthogonal transformation, eigenvalues and eigenvectors applicable to engineering problems. Eigenvalues and eigenvectors. Let A be a n into n matrix, that is n rows and n column matrix, x bar a non-zero n into 1 column vector, and lambda a scalar matrix. If A x bar is equal to lambda x bar, then x bar is an eigenvector and A of A and lambda is an eigenvalue of A. So, what are eigenvalues and eigenvectors? Let us see. Given a matrix A, x is the eigenvector and lambda is the corresponding eigenvalue. If Ax is equal to lambda x, A must be square and the determinant of A minus lambda I must be equal to 0. Trivial solution is if A determinant is not equal to 0. The non-trivial solution occurs when the determinant A minus lambda I is equal to 0. Are eigenvectors unique? If x is an eigenvector, then beta x is also an eigenvector and lambda is an eigenvalue. A beta x is equals to b a x is equals to beta lambda x is equals to lambda beta x.
Good morning. Myself Arya Thomre. My roll number is 65 and I am going to explain the topic of solving eigenvectors and eigenvalues when the matrix is non-symmetric and lambda is non-repeated. We will understand the steps of solving this type of problem using an example. The problem is as follows. Find the eigenvalues and eigenvectors for the given matrix for minimum value of lambda. The given matrix is 1 0 minus 1 1 2 1 2 2 3. Solution. Step 1. Consider the characteristic equation of matrix A as A minus lambda I equals to 0. It is represented as follows. Step 2. Consider the equation lambda cube minus s1 lambda square plus s2 lambda minus determinant of A equal to 0. This is the characteristic equation for matrix of order 3 by 3. Here s1 is the sum of diagonal elements and s2 is the sum of minors of order 1 of the diagonal elements of matrix. Now for the given example, the values of s1 is 6, s2 is 11 and determinant of A is 6. Substituting the values in the above equation, we get lambda cube minus 6 lambda square plus 11 lambda minus 6 equal to 0. Solving the above equation, we get lambda 1 equal to 1, lambda 2 equal to 2 and lambda 3 equal to 3. As the question says, we have to find the eigenvectors for the least value. Therefore, substituting lambda equal to 1, we get the matrix as 0 0 minus 1, 1 1 1 and 2 2 2 multiplied by the column matrix x, y and z, which equals to 0 0 0. Equations obtained from the above matrix is minus z equal to 0 and x plus y equal to 0. Substituting y equal to t, x becomes minus t. Therefore, for lambda equal to 1, we get the eigenvector as minus 1, 1 and 0.
Hello everyone, myself Janvi Sonar and my roll number is 61. Now in example 2, we have to determine eigenvalues and eigenvectors of following matrix A for maximum value of lambda. So in step 1, we have to consider characteristic equation of matrix A, that is A minus lambda I equal to 0, in which we have to subtract lambda from the diagonal elements. So matrix A becomes 4 minus lambda 6, 6, 1, 3 minus lambda 2, minus 1 minus 4 minus 3 minus lambda. And now step 2 is in which we have to consider lambda cube minus s1 lambda square plus s2 lambda minus determinant of A equal to 0, where s1 is the addition of diagonal elements of matrix A and s2 is the sum of the minus of the matrix diagonal elements of matrix. By finding s1 equal to 4, s2 equal to minus 1 and determinant of A equal to minus 4. Putting all these values in the equation 1, we get equation lambda cube minus 4 lambda square minus lambda plus 4 equal to 0. By solving the above equation, we get eigenvalues that are lambda 1 equal to minus 1, lambda 2 equal to 1, lambda 3 equal to 4, in which the maximum value of lambda is the lambda 3 equal to 4. We have to put this value in characteristic equation of matrix A. So equation becomes 0, 6, 6, 1 minus 2, 2, minus 1 minus 4 minus 7 x into xyz equal to 0. Let us consider first equation 6y plus 6z equal to 0. That is becomes y plus z equal to 0. By putting z equal to t, we get y equal to minus t. Now consider equation 2, in which x minus y plus 2z equal to 0. We have to put z and y values in this equation. We get x equal to minus 3t. And then for value of lambda equal to 4, we get vector like minus 3, minus 1, 1. And now next part will be explained by my friend Kaushal.
Hello everyone, myself Kaushal Sonje and I am going to explain about second type of eigenvalues and eigenvectors. In this type, matrix is symmetrical and lambda is non-repeated. Let's consider the following example. In this example, we have to find the eigenvalues and eigenvectors for minimum value of lambda. Solution. In step 1, we have to consider the characteristic equation of matrix A and A minus lambda I. In this, we subtract the value of lambda from all diagonal elements of matrix A. In step 2, we have to consider the equation that is lambda cube minus s1 lambda square plus s2 lambda minus determinant of A is equal to 0, where s1 is sum of all diagonal elements and s2 is the sum of minors of order 1 of diagonal elements of matrix A. Now, here s1 is equal to 8, s2 is equal to 4 and determinant of A is equal to minus 48. Now by putting all these values in equation 1, we get the following equation, that is lambda cube minus 8 lambda square plus 4 lambda plus 48 is equal to 0. Solving above equation, we get lambda 1 is equal to minus 2, lambda 2 is equal to 4 and lambda 3 is equal to 6. But we have to find the eigenvalues and eigenvectors for minimum value of lambda. So here minimum value of lambda is minus 2. So by putting minus 2 in matrix A, we get the following matrix, that is 7 0 1 0 0 0 1 0 7 into xyz is equal to 0. By solving this matrix, we get two equations, that is 7x plus z is equal to 0 and x plus 7z is equal to 0. By applying the Cramer's rule, we get x is equal to 0, y is equal to t and z is equal to 0. So, our eigenvectors are 0, 1, 0 for minimum value of lambda, that is minus 2. The next example will explain my friend Harshal Shirode.
Hello everyone, myself Harshal Shirode. I am going to explain about second type of eigenvalues and eigenvectors. In this type, matrix is symmetrical and lambda is non-repeated. Let's consider the following example. In this example, we have to find the eigenvalues and eigenvectors for maximum value of lambda. Let's see the solution. Solution is divided in two steps. In step 1, we have to consider the characteristics equation of matrix A and A minus lambda I. In this, we subtract the value of lambda from all diagonal elements of matrix A. In step 2, we have to consider the equation lambda cube minus s1 lambda square plus s2 lambda minus determinant of A is equal to 0, where s1 is equal to sum of all diagonal elements and s2 is equal to sum of minor of order 1 of diagonal elements of matrix A. Now s1 is equal to 3, s2 is equal to minus 90 and determinant of A is equal to 216. Put above values in equation number 1. That is lambda cube minus 3 lambda square minus 90 lambda minus 216 is equal to 0. Solving above equation, we get lambda 1 is equal to minus 3, lambda 2 is equal to minus 6, lambda 3 is equal to 12. But we have to find the eigenvalues and eigenvectors for maximum value of lambda. Here, maximum value of lambda is equal to 12. So put this value, we get following matrix: minus 14, 5, 4, 5 minus 5, 5, 4, 5 minus 14 into xyz is equal to 0. By solving this matrix, we get two distinct equations, that is minus 14x plus 5y plus 4z is equal to 0, and second 5x minus 5y plus 5z is equal to 0, that is x minus y plus z is equal to 0. By applying the Kramer's rule, we get the values of x, y, z. The values are x is equal to 9, y is equal to 18, z is equal to 9. Now we can write it as in the form of eigenvectors, that is 1 to 1. Next part will be explained by my friend Samruddhi Wagh.
Hello ma'am, good morning. Myself Samruddhi Vak. My roll number is 68 and today I am going to represent the topic of matrix is non-symmetric and lambda is repeated. In this type, if the matrix is non-symmetric and lambda is repeated, then the eigenvalues are linearly independent. That is lambda 2 is equal to lambda 3. We are putting z is equal to 0 to find the value of x2, and to find the value of x3 we are putting y is equal to 0. Let's consider this one example. Find the eigenvalues and eigenvectors for the given matrix for minimum value of lambda. We are finding minimum value of lambda, so here we are considering the equation of matrix and write the matrix again. In step 2, write the equation of lambda for 3 by 3 matrix, which is lambda raised to 3 minus s1 lambda square plus s2 lambda minus determinant of A, where s1 is the sum of the all diagonal elements, that is a11 plus a12 plus a13. Then find value of s2, which is sum of minor of order 1 of a diagonal elements of a matrix A. Then put all the s1, s2 and determinant values in the equation. So now we are putting s1, s2 and determinant of A into the equation of lambda. We get minimum value of lambda is 0. So we are solving the matrix for lambda is equal to 0, means value of lambda is equal to 0, which is the minimum value from the matrix. We are taking two dissimilar equations, which are x minus 6y minus 4z is equal to 0, and the second is 4y plus 2z is equal to 0. Now we are solving these two equations by the Kramer's rule. By solving these equations by the Kramer's rule, we get the values of x, y, z, which are x is equal to 2, y is equal to minus 1 and z is equal to 2, and we get the values. Similarly, we can calculate the eigenvalues for lambda is equal to 1, lambda is equal to 1, and by putting z is equal to 0, as I explained into the slide 1. Thank you so much.
Hello everyone, my name is Neha Nanasaheb Vadgule. My roll number is 67. Here I will explain type number 3. Matrix is not symmetric but the eigenvalue is repeated. So I will explain example number 2. So the example number 2, determine the eigenvalue and eigenvector of following matrix A for maximum value of lambda. Lambda is nothing but the eigenvalue. So step 1, consider the characteristic equation of matrix A, and this is A minus lambda is equals to 0. So Step number 2. Consider lambda cube minus s1 lambda square plus s2 lambda minus determinant of A is equals to 0. Consider this as equation number 1. So where s1 is the addition of a11 plus a22 plus a33 plus up to the an, and the s2 is a sum of minor of order 1 of diagonal element of matrix A. Now S1 for matrix A is 9, S2 is 15, and determinant of A is equals to 7. Put above value in equation number 1. So we get equation lambda cube minus 9 lambda square plus 15 lambda minus 7 is equals to 0. Solving the above equation, we get lambda 1 is equals to 7, lambda 2 is equals to 1, and lambda 3 is equals to also 1. Here we can see that the matrix is not symmetric, but the eigenvalue are repeated. Put these value in matrix. So first put lambda is equals to 7. We get equations. So by solving these two equations by using a Cramer's rule, we get the value of x, y, z such as 6, 12 and 18. So we get the eigenvector 1, 2 and 3. Similarly, we can calculate eigenvector for lambda 1, lambda is equals to 1, and the lambda is also equals to 1. So by putting z is equals to 0 for x2 and y is equals to 0 for x3. Thank you.
Hello, I am Jay Sindhwa and I am going to explain you the fourth type of finding eigenvectors and eigenvalues. That is, the matrix is symmetric and lambda is repeated. So, if the matrix is symmetric and lambda is repeated, that is lambda 2 and lambda 3 are equal, then the eigenvectors x1, x2 and x3 are orthogonal to each other. That is x1 dash into x2 is equals to 0. Similarly, for x2 dash and x3, it also equals to 0. So, to find x3, we consider x3 as LMN. So, let us consider with an example. Find the eigenvalues and eigenvectors for the given matrix for minimum value of lambda. So this is the matrix. So in the first step, we have to consider the characteristic equation of matrix A, that is A minus lambda I equals to 0. So take all the diagonal values and subtract lambda from it. In step 2, we consider again matrix equation, that is lambda cube minus s1 lambda square plus s2 lambda minus determinant of A is equals to 0. In this equation, S1 is the sum of diagonal elements, S2 is the sum of minor of order 1 of diagonal element of matrix A. Then we have to find determinant of A, which equals to 2, and we have to put this values in equation number 1, that is the matrix equation, and we get the values of lambda, and that are 2, minus 1 and minus 1. So put the value of lambda 2 equals to minus 1 in the characteristic equation. So we get 1 all the matrix. So equations will be x plus y plus z equals to 0. So consider z equals to 0 and take y equals to t. Therefore x will equals to minus t. So after doing the calculations, we get minus 1, 1 and 0. Similarly, for lambda 3 also, we assume that the eigenvectors x3 will be LMN. So, since x1 and x3 are orthogonal, which requires x1 dash is x3 is equals to 0, that is 1, 1, 1 into LMN equals to 0. So, we get L plus M plus N equals to 0. Consider this as equation number 1. Also, for x2 dash into x3, we get minus 1, 1 into 0 into LMN, and this equation is minus LM plus 0N equals to 0. So finally, by solving the equation, we get lambda 3 equals to 1, 1 and minus 2. Thank you.
Hello everyone, myself Altaf Tadvi. I am going to explain Kelly-Hamilton theorem statement. Every square matrix satisfies its own characteristic equation. The theorem states that if A minus lambda I equals to 0, example, Verify Cayley-Hamilton theorem for A matrix and use it to find A raised to 4 and A inverse. Step 1. The characteristic equation of A is A minus lambda I equals to 0. We have to subtract lambda from diagonal elements. Consider lambda cube minus s1 lambda square plus s2 lambda minus determinant of A equals to 0. Equation number 1, where s1 equals to sum of diagonal elements and s2 equals to sum of minor of order 1 of diagonal elements of matrix A. Now s1 equals to 5, s2 equals to 9, determinant of A equals to 1. Put above value in equation number 1. Equation number 1, lambda cube minus 5 lambda square plus 9 lambda minus 1 equals to 0. Step 2. By using Cayley-Hamilton theorem, we have a cube minus 5 a square plus 9 a minus 1. Now a square equals to matrix 1 2 2 minus 2 minus 1 3 0 0 minus 2 1 1 2 2 minus 1 3 0 0 minus 2 1. So equation become minus 1 12 minus 4 7 2 2 minus 8 1. A cube equals to a square into a. So equation become minus 13 42 minus 2 11 9 10 10 minus 22 minus 3. By using equation 1, a cube minus 5 a square plus 9 a minus I, we get 0 matrix. Hence Cayley-Hamilton theorem is verified. To find a raised to 4, we multiply equation 1 by a raised to 4 minus a minus 5 a cube plus 9 a minus a into I equals to 0. A raised to 4 equals to 5 a cube minus 9 a plus a. So equation become minus 55 104 24 minus 20 minus 15 32 32 minus 14 23. To find A inverse, we multiply equation 1 by A inverse. We get 2 2 6 1 1 2 2 2 5. Now next part will be explained my friend Ojas. Thank you.
Verify Cayley-Hamilton theorem for A matrix 1 1 3 1 3 3 -2 -4 -4 and use it to find A inverse. So the solution is step 1. The characteristic equation of A is given by A minus lambda I is equals to 0, that is 1 minus lambda 1 3 1 3 minus lambda minus 3 -2 -4 minus lambda is equals to 0. So the characteristic equation is given by lambda cube minus s1 lambda square plus s2 lambda minus determinant of A is equals to 0, where S1 is trace of the matrix and S2 is sum of minor of order 1 of given diagonal elements of matrix A. Now here S1 is equals to 0 and S2 is equals to minus 20 after calculation, and also determinant of A is minus 8. Putting above value in equation number 1, we get lambda cube minus 20 lambda plus 8 is equals to 0. So by using Cayley-Hamilton theorem, we have a cube minus 20a plus 8i is equals to 0. So finding a square is equals to minus 4 minus 8 minus 12 10 22 6 2 2 22. A cube is equals to 12 20 60 20 52 minus 60 minus 40 minus 80 minus 88. By using equation 1, a cube minus 20i plus 8i is equals to, we get a null matrix. Hence Cayley-Hamilton theorem is verified. To find A inverse, we multiply equation 1 by A inverse. We get A square minus 20i plus 8A inverse is equals to 0. So A inverse is equals to 1 by 8 into 20i minus A square. So here A inverse is calculated 24, 8, 12, minus 10, minus 2, minus 6, minus 2, minus 2, minus 2.
Hello, myself Raj Varde. I am going to explain the topic that is diagonalization of matrix. Find model matrix P which diagonalizes the matrix 1 minus 1 minus 1 1. Step 1. The characteristics equation of matrix A is A minus lambda I equal to 0, that is 1 minus lambda minus 1 minus 1 1 minus lambda. We have to consider equation that is lambda square minus s1 lambda plus determinant of A equal to 0, equation number 1, where s1 is addition of diagonal elements and determinant of A equal to 0. Put above values in equation number 1. Lambda square minus 2 lambda plus 0 equal to 0. Solving these equations, we get two values for lambda, that is lambda 1 equals to 0 and lambda 2 is equals to 2. For lambda equal to 0, let eigenvector be x1 equal to xy, and then matrix equation becomes 1 minus 1 minus 1 1 into xy equal to 0 0. We get x minus y equal to 0 or x equal to y, x1 equal to 1 1. For lambda equal to 2, let two eigenvector be x2 equal to xy, and then matrix equation becomes minus 1 minus 1 minus 1 minus 1 xy equal to 0 0. We get x plus y equal to 0 or y equal to minus x, x1 equal to 1 minus 1. Thus the model matrix P equal to x1 x2, which diagonalizes A, is P equal to 1 1 1 minus 1, and D is equals to lambda 1 0 0 lambda 2 equal to 0 0 0 2. Thank you.